and welcome back to Calculus 1. We are continuing section 3.7 on chain rule. So this is part 2. Last time we said that if you have function composition, the way to find the derivative is to use the chain rule. Now, last time we only dealt with basic cases. Yeah, you might argue the stuff is not easy, but that still is, those are basic cases. We have two ways in which we can improve the fun. Number one is what happens if we are to to compose more than two functions. What if we had 4 functions that are nested? Can we take the derivative of that? And the answer is yes. Theoretically, you can chain any amount of, nest or compose any amount of functions, and the formula and the procedure will still be relevant. Now, I want to just work out one of the basic examples from yesterday so that we can continue this lecture and then upgrade those concepts. So first, we said if you have the derivative of, and let's over here say you have x cubed plus 3x minus 6 raised to the 5th power. We said what I'm going to do is I'm going to disregard what's inside. It's just going to be like x to the 5, and I can deal with that. And then I will take the derivative of x to the 5, but instead of x I will write whatever I scratched out. So the derivative of this must be 5 times, and then we put the inside raised to the 4th, and then times the g prime, which is the derivative of the inside, which is 3x squared plus 3. Now in this situation, you will be setting this equal to 0 eventually in chapter 4. You should not be multiplying this out. What you should do is actually just kick 3 outside of the parenthesis, right? And make that into a 15. You don't have to, but it could be done. So if you are to do anything and make this better, you would kick 3 outside, and everything else would stay the same. Now when you set these guys equal to 0, you'd have some simple equation. Well, these are polynomials. They're not simple ever, but yeah. So the formula that we used was that the derivative of function composition, where you plug in g of x into f, is the derivative of the outer function with g plugged in times the derivative of g. So that was the formula which we used all along. Now there is another way to write the same idea, and that is that you have this function f that has g plugged in, right? But you are looking for df dx, right? So you're looking for the derivative of function f, and then that function f happened to have g plugged in. So you're technically looking for the derivative of f in respect to g, and multiplying that with the derivative of g in respect to x, which is exactly what you have. Now, if you are observing the formula written in this way, you see that these dg's actually cancel, and you have df dx equals df dx, right? So we can represent chain rule in this fashion as well. And observe that the derivative was done in terms of dg. So if I am to go back to my previous example up there and write it as what is the derivative in respect to x of some g of x raised to the 5th power, you can still do it, because you will still say, oh, it's 5g of x to the 4th times the derivative of g of x, right? Which actually you can also see in the blue boxed equation as well. So you don't necessarily have to know what the inside function is. It could be anything, right? As long as you know it's a function of the variable that you ultimately are after, which is x. right? It has to go with a times g prime. We are going to use this in two sections, this idea, in two sections that are coming up. Now, the next part here is to elaborate on the blue box and say, now, compose more than two functions. Let's, for the sake of argument, let's do 4. All right, it's fine. Let's do 4. So say you are trying to take the derivative of f, of g, of h, of k, of x. So that's 4 functions. So what would be the derivative of this? Well, we have a formula that we can either write in terms of f of x, like the red box, or the one in terms of df dx in the blue box. And I'll write both. So the derivative of this would be the derivative of f with all of this plugged in. Oh, I have one extra parenthesis there, right? This goes with this, yeah. So f prime. So g of h of k of x times, now you go the derivative of the inner one, which is g prime, but then g prime had h and k in it, times the next one in, which is h prime of still k of x, and finally times k of x prime. How do you know when to stop? Well, you need to know how many functions are chained, and that's how many, how many functions are composed, and that's how many chains you have. So we have 4 functions, right? Therefore 1, 2, 3, 4 of these. That should always match. Now, much better way to write this formula would be to say, what is the derivative of f of g of h of k of x, and then you close all these parentheses. And the answer to that would be, oh, it's simply df dg dg dh dh dk dk dx. It is much better formula to write because it's far less writing. And this is if you chain 4 functions. You can kick out k, then you have 3 functions. You can add another variable, have 5. So whatever. Here's an example of this. What is the derivative of cosine cubed of x squared? Right. What do you think? How many functions is this going to chain now? That's 90% of your skill, guys. All right, the 10% is take the derivatives. 90% of your skill is to recognize how many functions, what they are, which order. Right, that's 90% of the skill. So pre-calculus 1 is 90% of this skill. And then 10%, do you know what the derivative of cosine is? How many functions do I have? 3. What is the most outer function? We'll call that f. X cubed, nice. What's the next one in? Cosine x, very good. And what's the last one? X squared, very good. Now, how do you check this? Well, you take this, you start from the bottom. Plug x squared for x, and you get cosine x squared. And then plug in cosine x squared for x in f, and you will get cosine cubed. First off, if you are confused by this, please learn once and for all that sine or cosine to the nth power means this. All right? So if you are having issues, this is most likely the issue that you have. You don't know the notation. Same thing goes for ln. ln to the nth power of x is ln x to the nth power. And these are different than saying sine x to the n, because the top one will say sine times sine times sine, where the other one is sine of x times x times x. So it is important whether this n is here or here, right? It's a completely different function. Now, these two notations are the same, and this one will be different than those. So make sure you are able to spot that right away. And I did have a problem yesterday to make sure you are understanding the difference between sine cubed x and sine x cubed. As you can see, completely different answers in the back, because the order of functions is different, because that cube matters. The first one has sine times sine times sine. The second one has sine of x times x times x. So they're different. So now when I have these more complex problems, like this one, this plays a big role in deciding which function is on top, which function is the first and in charge, and then what's inside and what's inside. In the very simple, if you need to visualize, the function composition, just let's say money has function. You put that in a wallet whose function is to organize money and cards and stuff, and you put that wallet into your bag, which has function to keep all of your stuff in one spot, right? And all of a sudden money is in the wallet, wallet is in the bag, and there's your triple link. All right? All of these things had functions. Now, they're not functions in terms of numbers that you are used to. They're functions in terms of, they have functions in another way, but it's a function nevertheless, right? So now we have this part where we plug one thing in another, we chain it, and we have this particular thing. So now I'm going to start derivatives. First, I need to find the derivative of x cubed. Now, that is going to eliminate this cube on top. The rest is staying the same. So I'm going to have 3 cosine x squared, everything squared. So that is my first step. Now I have to take derivative of the inside. Well, derivative of cosine is negative sine, and I have to keep x squared. And finally, derivative of x squared is 2x. Now, time for me to check this, right? I have 1, 2, 3 functions. I have 1, 2, 3 in my derivative. We are all good. Now I just need to make this beautiful, and we are done. So I am going to say 2x times 3 is 6x in front. Then I have cosine squared x squared. I have sine x squared, and the minus is going to go in front of the 6. And there we go. So this is the derivative. You are finally ready to say equal to 0 in chapter 4. The first term will give you 0, second term will give you something, this one will also give you 0. All right, so you are going to be able to solve this. But clearly, in order for you to solve this, you first have to be able to find this derivative. And one more of these, and then we are going to change things again. Now I would like to see something from the book. Oh, this is nice. I mean, you know what I mean. Find the derivative of tangent of e the square root of 3x. This is problem 51 in your textbook. Please decompose, okay? So decompose this and then do the rest. Okay, let's take a look. How many functions? 3. So the outer function f would be what? Tangent x. Very good. Then one level in, e to the x. Very good. And then the last layer. Okay, so square root of 3x. Sure. You can write this as, well, we can do 4. This could be square root of x and then, when you can't decide. Sure. 3x, it's a linear function, it's oblique line, right? Goes through the origin. So whether you did 3 or 4, I don't care. You do have to have that times 3 at the end. So as you take this derivative, you better have that times 3 at the end. But you might not have done that. I don't know. Let's see. The derivative of tangent is secant squared x. So we start with a secant squared of e to the, right? We have to copy the argument of tangent exactly the same, right? Because we are not working on it. Now times the derivative of e is itself e. So you get to copy this thing, and now you have to take the derivative of the exponent. Now that's the derivative of square root. You know that's 1 over 2 square root, and you have to put 3x there. And then finally the derivative of 3x is 3. Woohoo. There it is. So now what do we have? To make this more compact, we have 3e square root of 3x divided by 2 square root of 3x times secant squared e square root of 3x. So what we should be seeing here, 1, 2, 3, 4, 1, 2, 3, 4. Bueno? All right. Let's take a look at the next step. So to further make chain rule interesting, we are going to combine chain rule with other rules, right? And the other rules are, let's say, the product rule and quotient rule. I would like to give some motivation because much of chapter 3, apart from the 2 applied sections obviously, is dry and boring, pretty much like algebra. We learn all of these shortcut methods, just like memorizing multiplication table, because someone, in this case me, told you it's going to be eventually useful. Last class we've seen some business applications, and we are moving towards 3.11 where we will see a lot of cool stuff. But for now, who cares about chain rule, who cares about product rule, who cares about all of these things? Well, let's just take a look at one of the applied problems. I know this is not in the realm of all of you, but it at least explains something that you have understanding of. So, if you have an object that is hanging off of the ceiling and you hit it a little bit, it will start bobbing left and right, and then as the time passes, it will slow down, it will have less of the outward movement, and it will eventually stop and stay still. So the object would be hanging off of the ceiling, whatever you have on the other end, and as you hit it, it will be moving between these two locations like this, right? We call this simple harmonic motion. It will be going back and forth, but it would actually eventually stop. Now, the trick over here is to observe how far out it goes. And we can model that motion of how far it goes using a simple equation. And that simple equation would be, say, e to the at cosine. Actually, no, let's do sine because I'll explain that. Sine bt. So this is called, well, I need a negative over here. So this is called, and I'll just put that a and b are positive numbers. So we can measure how far this object goes in time with this equation. Now, if you are to graph something like this on your graphing calculator, you will get this. For the t-axis and for the y-axis. So the distance, because it's sine, it starts at 0, and initially when you hit it, right, to one of the sides, let's say to the positive side, so it goes first over here, right, this distance is largest, and then it goes back, it lost some of the energy, and then the other side will be less, and that's why this peak over here is higher than this peak over here. And I can see that every consecutive peak is going to be smaller and smaller in size until it completely dies out and stops. So this is something that you all observed just because you were alive and there were things that are hanging. Maybe you hit it with your head passing through, like a, I don't know, chandelier or whatever, and it was bobbing for some time and then it stopped, right? So observe the function up there. Do you see that that's two chain rules? Right? You have the AT and then you have BT. Those are chain rule. Yeah, they're basic, but they're still chain rule. And it's within the product rule, right? So this part of the equation gives us the oscillation part, right? But if it was only sine B, it would never stop. It would always go the same height. And then you have the what we call the decay part, right? Which is the one that actually makes it stop. So these two together, we call this damped oscillations. You will learn much more of this in differential equations if you take the class. You see that taking the derivative of this is actually the product rule with two chain rules inside. So what is our y prime in this case? We are taking the derivative of y in respect to t, and we are dealing with the product rule, right? Because you have function times another function. So I'll write here in blood, need product rule first. Need product rule. So what's the product rule? The product rule says copy the first, which is e to the negative at, times the derivative of the second, well, that's cosine bt times the chain, which is b. Plus, from the product rule, copy the second one as is, which is sine bt, times the derivative of the first, well, the derivative of e to the negative at is e to the negative at, times the derivative of the top, which is this. Now, why would you want a derivative? We did that yesterday. Why would you want a derivative? If you have a position function over there in time, what do you learn from the derivative? What do you get when you take derivative of position? Velocity. Holy nightmare. So velocity is going to be b e to the negative at cosine bt minus ae negative at sine bt, and now we make it, right, we factor, make it easy. E to the negative at is common, and in parentheses we have b cosine bt minus a sine bt. And with this formula, right, so you will observe, again, in differential equations and physics, right, you will observe the period of how fast, right, what is the time that it goes, and that would be giving you b. and then this A depends on the conditions in terms of the air resistance and all of the other stuff, the shape of the, but you will have numbers as A and B. So let's say they're -3 and 4, right? So you will just put -3 and 4 and 4 and -3 and 4, right? So that's that. So that's some motivation for you to see that, you know, these things are actually used. In mathematics, we generally, you know, come up with theories because we can, and then eventually someone figures out how they fit into the reality. So currently our technology is utilizing mathematics that it's developed in 1800s, right? So technically, and some stuff from linear algebras for computers from 1900s. None of the current mathematics that it's developed is utilized in any way. Generally, technology is lagging about 150 years. So all of our technology today is based off complex numbers, right, which are two-dimensional numbers. You have the real part and imaginary part. So those are considered the two-dimensional numbers. And AC current, right, which was conceptualized, developed by Nikola Tesla in late 1800s, that's all based off of the complex numbers. Today we have hyperdimensional numbers, right? You have a number that has like 18 dimensions, right? We have zero application for it today. But, you know, give it 150, 200 years, there will be some amazing stuff, right? So as much as electricity that powers everything we have on this planet today, as much as it's awesome and just, it's there for us, right? You panic when you don't have it, obviously, but, you know, you don't even notice it on a daily basis. Just think about, just go 100 years ago. People were still using oil candle lamps and candles just 100 years ago, right? And then, I mean, infrastructure was developing, right? 200 years ago, everyone was using candles for light. But, you know, just 100 years ago, the vast majority of population did not have electricity, right? Today, a lot of people still don't have it, but, you know, vast majority of us does, So now let's take a look again at these just abstract, pointless problems. So they're not going to be applied as this one was applied. But, you know, these problems that we are going to take a look again, they're just, you know, practicing your skills. So, for instance, problem 58 says, find the derivative of e to the x divided by x plus 1, everything to the 8th power. So which two rules are we combining in this problem? Okay. Chain and quotient. Very good. Now, which one is within which? Is it chain within quotient or quotient within chain? Quotient within chain, because this 8 is on the outside. So chain rule is the main rule, and then when you have to take the derivative, you will be dealing with the quotient rule. So technically the big skill to see here is that this is x to the 8th, right? As soon as you see that, then you know that you will be taking the derivative of this x, and that's when quotient rule kicks in. So I have 8 e to the x over x plus 1 to the 7th times the quotient rule, which is x plus 1 times the derivative of e to the x is e to the x minus e to the x times 1 divided by x plus 1 squared. And now we simplify this. Well, first over here is x e to the x plus e to the x minus e to the x, so they cancel. So what we have is 8 e to the x over x plus 1 to the 7 times x e to the x over x plus 1 squared. Now what I'm going to do is some of the mathematical gymnastics now to compress this. You see this fraction over here, right? This fraction can be broken up into x over x plus 1 times e to the x over x plus 1. And now this e to the x here is the same as this guy. So I'm going to put them together in the same power. So what I get now is 8 times e to the x over x plus 1, and now to the 8th power, because I'm bringing this one in, times x over x plus 1, for the total of 8x divided by x plus 1 times e to the x over x plus 1 to the 8th. Why do I want to simplify this? The more I simplify, the easier it is to set it equal to 0 and do chapter 4. That's the reason. All right, problem 60 is asking you to find the derivative of tangent x e to the x. So we'll do this problem one more and chain rule is officially done. So what do we have here? What do we have here? We have some functions, right? Can anyone tell me what we have? Product inside of the chain. Good. Whew. So, product inside the chain. There we go. So we are going to take the derivative of tangent, which is secant squared, and we have to copy the same argument. And now we have to take the derivative of the inside, and this is where the product rule kicks in. Copy the first, derivative of the second, plus copy the second times derivative of the first. So as you can see, this takes a lot of practice, guys. Kick e to the x outside, you're left with x plus 1 in parentheses, and then we have the secant squared, x e to the x. So, you know, I think this is where your weekend is going. Right. About 5 hours of this, you should be good. You can write anything down. That's the best part. And then you can go and ask software to tell you if you're right once you're done with it. You can literally put anything. Now, I'm going to write something down, and then I'm going to ask you to wait. Imagine if you are to take the derivative of x squared minus 1 to the 4th power times the cube root of x to the 6 minus x plus 5 divided by x cubed sine to the 6x. I hope that you see 3 chain rules, right? Everything except x cubed is a chain rule. That you see 2 separate product rules, one on top and one on the bottom, right? And then overall quotient rule. So if you are to write this the way we know, you would have to start working on the quotient rule first. And then when you, within the quotient rule, you will have both derivatives of top and bottom. So that will be the product rules. And then within those product rules, you will be taking the derivatives of each individual one, which would hit you with the chains. A problem like this should take about 20 minutes or so. You wouldn't, right, go any extra. Now, what if I told you that some of you, with few hours of practice, would be able to take the derivative of this mentally, without writing anything down, and give the answer in a factored form? And if you can do that with this, you can do that with every single derivative that we learned so far. That you can be so powerful, right, when it comes to taking derivatives, that you would not need paper or a pen, and every time you would give your answer in a factored form. Wouldn't that be cool? Yeah. So we're going to learn that technique because it's a part of one of the lectures. Now, the author tucks that in as a, you know, small part of the lecture, and they give you 4 homework problems. But that is the most powerful derivative taking technique which you could master and just keep freaking people around. I mean, obviously, you show up in Calc2 and then you take the derivative that way just by looking at it, and everyone goes, what? And I actually know even of professors who don't pay attention to it either. So, yeah. So we are going to learn a method eventually in this chapter. It's coming up. So it's either going to be today or tomorrow. I believe it's tomorrow. Where you would be able to do that. And then you will obviously choose to just, learn the bare minimum of that method and just survive the 2 problems, one on exam and one on the final. Or you would actually invest insane amount of time, and if you invest this insane amount of time, you would have that power. So I'm going to leave it at this. Those of you that are really aggressive and thirsty for knowledge, we'll actually spend 20 minutes, 30 minutes, an hour, whatever it takes you at this stage of the game, probably an hour, to try and write this one out as a channel. It should be your notebook in a landscape mode, and you still to take probably 2 lines to write it out. So yeah, it's going to be disgusting, I promise you that. But it's going to be a very valuable learning experience, primarily in what not to do when you see a problem like this, right? And then we are going to cover a technique that will, have a substantial amount of reduced work, but then also you can learn how to mentally take care of any derivative ever, and we'll eventually get there. So this ends talk on the chain rule. The next section is on implicit differentiation 3.8. So let's take a few minutes and then deal with that section when we come back.